So first I'm going to talk to you about acid-base titrations at a high level, and then in a few minutes we'll get more into the details of our exact titration that we're going to perform. So what titration is it's a technique where you use a solution of known concentration to find the concentration of an unknown solution. So if you recall from the limiting reactant lab where we worked with baking soda and vinegar, we had talked about in lab that vinegar is only 5% acetic acid. The other 95% of it is water. So if you had 100 grams of 100 grams of vinegar, 5 grams of it would be acetic acid, and the other 95 grams of it would be water. And if you look at the label here on a vinegar bottle, it says that it's 5% acidity. The 5% acidity means it's 5% acetic acid. That, however, is just an approximation. So we know it's about 5% acetic acid in vinegar, but we can use titration to figure out the exact concentration. So maybe we're going to find it's 5.16% acetic acid or 4.85% acetic acid. So that's the goal of the experiment. So the question, exactly how much acetic acid is in vinegar, can be rephrased as, what is the concentration of acetic acid in vinegar? Now, in order to find the concentration of acetic acid in vinegar, we need to have one solution where we're going to know its concentration exactly. So what we're going to use is we're going to be using sodium hydroxide, and we're going to know its concentration exactly. And then we'll use that to determine how much acetic acid is in vinegar. And we can do that because sodium hydroxide is a base, acetic acid is obviously an acid. So we're going to use the base to neutralize the acid. And when all of the sodium hydroxide has neutralized all of the acetic acid, we'll then be able to calculate and determine how much acetic acid there is in vinegar. So let's talk about exactly what happens during a titration. So I have a little illustration here. So what we're going to use is we're going to be using a burette. The burette is the long, narrow piece of glassware. It's very accurate and very precise for delivering liquids. And then we'll be using an Erlenmeyer flask to hold our, initially hold our vinegar. And so the burette will be filled with our sodium hydroxide. And like we said, it will be of known concentration. And the Erlenmeyer flask, we're going to be putting in there 2.00 mLs of vinegar, which we'd put in with a volumetric pipette because we want to put it in very accurately, very precisely. And we'll also be adding 3 to 5 drops of this phenolphthalein indicator, which is a word with way too many consonants. But what the phenolphthalein indicator does is it tells us, and it tells us by changing color, it changes color when there's base present. So initially, we'll put our 3 to 5 drops of phenolphthalein indicator in with the vinegar, and because vinegar contains acetic acid, the phenolphthalein will be colorless because it's colorless in acidic conditions. Now we'll start adding base, and once we've added enough base to neutralize or react with all of the acetic acid, that phenolphthalein will turn pink and will indicate to us that that is the end point of our reaction. So before we start the titration, we will fill the burette with sodium hydroxide. And like I said, it will be of known concentration, and we'll talk about how we determine the concentration of sodium hydroxide when we discuss the calculations, but we'll know the concentration of it exactly. And so our burette would be filled, and what we would do is we'd have to take a reading. We'd have to know our initial VI, initial volume of sodium hydroxide. So we would have to read that, and we'd read it at the bottom of the meniscus, and we'd read it to 2 decimal places. So let's just say, for instance, that our initial volume here is 5.83 milliliters. So we know our initial volume. And so then you can see that the Erlenmeyer flask right now just has some vinegar in it, and I've shown that by making it kind of a silver color because initially the vinegar is going to be clear. It's just going to look like water. Even though we have our phenolphthalein indicator in there, it will be still colorless because that is an acidic solution. So then what we're going to do is we're going to start adding sodium hydroxide into our Erlenmeyer flask by opening up the stopcock on the burette, and we'll add it slowly. And what we're looking for is we're looking for our solution to start to turn pink. And so as our titration proceeds, our flask fills up more and more because now we have a mixture in here of our vinegar and our titrant, which is our sodium hydroxide. So just for definitions, the sodium hydroxide, this is our titrant, and the vinegar, or specifically the acetic acid, is our analyte. So we have our titrant and our analyte. We're using the titrant to find the concentration of our analyte. So our solution at this point is still clear. It's still clear because we still have acidic conditions right now. And so if you look at our balanced chemical equation that describes the reaction between sodium hydroxide and acetic acid, at the beginning of the reaction, what you have is you have excess acetic acid. So you have more acetic acid than you have base. So in the flask right now, because it's still clear, and the phenolphthalein tells us if we have acidic conditions or basic conditions. If it's clear, or I should say if the phenolphthalein is colorless, then we have excess acid. So every time we add a drop of sodium hydroxide to our flask, it reacts with the acetic acid to give us water. But because we still have more acetic acid around, the solution is still clear in color. Now, what we do is we keep adding drops until eventually you start to see these pale pink streaks appear in your solution, and they appear and then they disappear, and they appear and they disappear. What that means is you're getting very, very close now to having enough sodium hydroxide to react with all of your acetic acid. Then at some point, what's going to happen is we're going to add one more drop of sodium hydroxide, and all of a sudden, the NaOH would be in excess. We'd have more sodium hydroxide than acetic acid. So the sodium hydroxide would react completely away, would react with all of the acetic acid, and we'll be left with some sodium hydroxide. When that happens, we know that happens because our indicator solution will tell us. This entire solution will turn a very pale pink, and it's going to be paler than what I'm showing. This is kind of a salmon color. But our whole solution turns a very pale pink, and what that means is we have NaOH in here and no more acetic acid. And so as soon as we see that solution turn this very pale pink color, we stop adding any more drops of our titrant, and we're going to go ahead and we'll read the volume again. So this time we have to read the volume again at the bottom of the meniscus, and we'll read it as a final volume. So let's say that we have 15.96 milliliters. That's our final volume. And this is good. So the reason we wanted to perform this reaction is we want to know exactly how much sodium hydroxide it took to react away all of our acetic acid. So if we want to know how much we added, well, our change in volume, or we can say volume added, is equal to our final volume minus our initial volume, and that would be equal to 10.13 milliliters. And so this is final volume minus initial volume. And so once we know how much sodium hydroxide we added, and we know the concentration of sodium hydroxide, then that will allow us to calculate is we'll know how many moles of NaOH we needed to react away all of the acetic acid. And since out front here, it's 1 mole of sodium hydroxide reacts with 1 mole of acetic acid. Say, for example, say we had, say we calculated that we had 0.5 moles NaOH is what it took to react away the acetic acid. That means we know that we had 0.50 moles of acetic acid initially. So me saying we have 0.5 moles of sodium hydroxide, I don't know that yet. That's probably not the case. We'd actually have to calculate this, but it's just an example. So what we're going to do now is we're going to talk about how we would go about calculating the initial exact concentration of sodium hydroxide, how we would calculate the number of moles of sodium hydroxide that it took to react away all of the acetic acid, and then how we would calculate how many moles of acetic acid were present initially. Okay, so before you go on and watch the titrations part 2 video, just a few notes about this lab. Lab 9, which is titration of vinegar. This is your last lab for the semester. This lab report will be due on Friday, May 1st, and the post-lab quiz will be due at 2 o'clock on Wednesday, April 29th, which is the last time before our first lab meeting of that week. Before you go and watch the part 2 video, please read the introduction in your lab manual for this laboratory. Read section 8.7, which is titrations in your textbook, and also watch the short 2-minute video that I have in the lab manual on acid-base titrations. It's interactive 9.3. And then before you watch my part 2 video, you do need to have a data table someplace in your lab notebook. If you're doing it by hand, you can do this in Notability if you're going to do your lab report there. So data table, what you need is 3 trials. You need the volume of a spot for the volume of vinegar, initial burette volume, final burette volume, and that's the data you'll record during the lab. And then the volume of sodium hydroxide added, that's actually a calculated column. That's going to be final volume minus initial volume, just like we demonstrated in this video. So now you should go ahead and take a break, and when you're ready, we will meet you right back here.